Sauce here. This is a video lesson on examples of using the fundamental theorem of calculus. The fundamental theorem of calculus is the integral from a to b of a function f of x with respect to x is equal to the antiderivative of that function evaluated at the upper bound b minus the antiderivative evaluated at the lower bound a. The fundamental theorem of calculus, this is technically part 2. Part 1 was thinking of a definite integral as an area function that then allowed us to produce this, which is useful because it shows us how to process the definite integral and come up with a value or an answer. That's the general property. Let's use it. For example, the integral from 0 to 2 pi of the function sine of x with respect to x. This definite integral, the value that we will be able to evaluate from this represents an area between the sine function and the horizontal axis. We can get an idea of that area before we process the definite integral or use the fundamental theorem of calculus so that we can check our answer. We're going to figure out what we should expect to get before we do it. This is a sine function. This is a graph of sine. And the bounds of integration from 0 to 2 pi is one complete period of this sinusoidal wave. And because of symmetry, the area that is above the x-axis is positive and exactly equal to the area that is under the x-axis, which is representative as a negative quantity. Area can't be negative, but the area under the curve, which is representing this integral or a piece of it, can be represented as a sum of negative values. So what should we expect to get when we integrate one period of sine? We should expect to get 0 because these two regions of equal value and opposite sign are going to cancel each other out. So we know where we're going. Let's see if we can get there using the fundamental theorem of calculus. I need to find the antiderivative of sine of x. We know that the derivative of sine is cosine, but we're going in the inverse direction. The antiderivative of sine is a negative cosine of x. Taking the derivative of a negative cosine of x would reproduce what we started with. And we're going to evaluate this from 0 to 2 pi. We're going to use the symbol pipe, and we're going to put the bounds of integration that we need to use with this antiderivative. This is an intermediate step. This pipe symbol means evaluate at. And we often use it when we are showing a solution process of the definite integral, because our first thought ought to be finding the antiderivative, and then afterwards we want to apply the bounds. But we still need to represent the bounds of integration in this step. That's how we do it. Now I'm going to evaluate the antiderivative at the upper bound. Again, the fundamental theorem of calculus, we find the antiderivative and we put the upper bound into it. That will be negative cosine evaluated at 2 pi. And then we're going to subtract the same antiderivative. So be careful, we're going to subtract a negative, I'll use parentheses, minus the antiderivative of sine evaluated at the lower bound, 0. I'm going to simplify. It would help to remember what the cosine function looks like. It starts at 1 and it is slightly out of phase with sine, cosine comes back up to 1 at 1 period after 2 pi. The two values of cosine that we're interested in are 0 at 0 and at 2 pi to evaluate these. The negative of cosine of 2 pi is -1, and we're going to subtract a negative or add the cosine evaluated at 0, which is also 1. And I can combine these two terms. -1 plus 1, of course, is 0. The area under the curve of sine from 0 to 2 pi is 0. That's what we expected. These two regions canceled each other out. Let's see another example. How about evaluating the integral from 1 to 2 of radical x plus x squared with respect to x? We want to find the antiderivative of radical x plus x squared. And then we're going to put the bounds into it and produce a final value. The antiderivative of the sum of these two terms is going to be the antiderivative of each added together. The antiderivative of radical x, we want to think of x as the power of 1/2 and use the power property for integration, which means that we're going to add to the exponent. So the exponent of 1/2 raises to 3/2, and then we're going to divide by the new exponent. So we're going to divide by 3/2, which is the same thing as multiplying by 2/3. So I'll put 2/3 out front to multiply. 2/3 x to the 3/2 is the antiderivative of radical x. Finding the antiderivative of x squared uses the power rule for integration, raise the exponent by 1, and divide by the new exponent. Now that I found the antiderivative, I'm going to include in this step of work the bounds that I have to apply using the pipe symbol from 1 to 2. And then I put the upper bound 2 into the antiderivative to get 2/3 times 2 to the 3/2 plus 2 to the 3rd divided by 3. And I'm going to subtract now the antiderivative evaluated at the lower bound, which means putting 1 into this. Careful, there's a negative to distribute, so I'm going to use parentheses. Putting 1 into the antiderivative is 2/3 times 1 to the 3/2 plus 1 to the 3rd divided by 3. And I can finish up by evaluating and combining. 2 to the 3rd is 8. And then the square root of 8 is radical 8, still multiplying by 2/3. Plus 2 to the 3rd is 8, divided by 3 is 8/3. Minus 1 to the 3rd is 1, the square root of 1 is still 1, and 1 times 2/3 is 2/3. Distributing the negative of 1 cubed over 3 is 1/3. I've got some fractions with a common denominator to add, so I can express the final answer as 2/3 radical 8 plus 8/3 minus 2/3 minus 1/3 leaves 5/3. This is about as simple as it can get. We'll stop there.